Okay, this is Dr. Kraus again talking about some tips for Lab 3. I've had two different groups ask me questions that had pretty similar answers, so I wanted to make sure that we kind of dealt with that so that you're ready to do the lab. And so the issue is basically that there are a couple of quirks associated with the FFT that are going to lead to you getting results that are maybe slightly odd or counterintuitive. And basically it boils down to two things. The DC component, so if you have a sine wave and it's offset so that it doesn't have an average value of 0, the electrical engineers would call it the DC component. It's a constant shift that doesn't have a sine or cosine with it, although in the FFT world it shows up as the coefficient of the very first cosine term, where you'd have the cosine of 0, which works out to be 1, times something to give that DC component. But what comes out of the FFT is actually twice the number that you would expect. The other issue is that the sign of the sine terms is the opposite of what you would expect. So the SIGN of the SINE terms is off by -1. So if I have this symbolic expression, and maybe this will be a little bit weird, but I think it's also good practice for your FFT-related quizzes. I want you to understand how to find the FFT results when you know what the answers should be. And when you get those kind of test cases working correctly, then I feel like you're prepared to handle real data. So I ask you a lot of questions sometimes about fake data so that you know how to correctly interpret the results so that you're ready for real data. So we've got a cap T here of 0.1 seconds. That means that our DF is going to be 10 hertz. So I'm only going to have values every 10 hertz, and so I've deliberately chosen a cosine wave at 20 hertz and a sine wave at 40 hertz. So my frequency vector should work out to be 0, 10, 20, 30, 40, 50, 60, 70, 80, on and on, up to 990, because I've got a sampling frequency of 1,000. So I expect that FFT results to have 3 non-zero values and then 2 aliased values. So there'll be a non-zero term for the DC component for the 0th cosine term. There should be a value of 3 corresponding to F equal 20 hertz on the A coefficients, and there should be a value of 5 corresponding to 40 hertz on the imaginary parts, the B coefficients, but it will actually work out to be -5. So I'm going to plot this waveform when I run this code. I've already run it, and so the waveform looks like that. It has the 2 different frequency components, one at 20 hertz, one at 40 hertz, and then, like I said, it also has a non-zero DC value of 7. And so that's the waveform. And then I get its length, and I properly scale my FFT. I create a frequency vector. So this NVect has the values 0, 1, 2, 3, 4, 5, 6, 7 up to the length of the T vector, and then I just multiply that by DF to get my 0, 1DF, 2DF, 3DF, 4DF, 5DF. So if we look over here, NVect goes from 0 to 99, and so freak goes 0, 10, 20, 30 on up to 990 because DF is equal to 10. And then I wrote this little function that I don't actually use yet, but I'll show you that in a second. And then I take that FFT and I want to look at the real coefficients, which are my cosine terms, and the imaginary coefficients, which are the negatives of my sine terms. So if I run the code, I get this FFT, which it's maybe kind of hard to see, but there's a non-zero DC value, and there's a non-zero value here corresponding to a frequency of 20. We'll zoom in a second. And then an aliased version over here at 980. And then those have amplitudes of 3, which corresponds to what we know. We should expect that the 3 cosine whatever times 20 hertz is going to give me a waveform, or a peak at 20 and a peak at Fs minus 20, which is 980. And then the sine term will give me a peak at 40 and at 960. And so we see this guy here is 960 with a y value of positive 5 and a y value of negative 5 at 40. And so let's do zoom in on that just to be real clear. And so there we are. Negative 5 at 40, positive 3 at 20, and 14 at 0. Like I said, there's a factor of 2 here and a negative sign here that we need to deal with. So if we wanted to reassemble this thing, we might do something like, I'm going to take the real indices to be where the real of y FFT, and I guess I'm going to go the ABS of the real because I want to allow it to possibly also be negative. Where that's greater than, say, something kind of small, and the 0 of that, and the IMAG INDs do the same thing, but have it tell me the imaginary parts. So if I run that, and I look at my real INDs, that's pretty good. That's all of them. That doesn't make any sense. Oh, whoops. I have pluses in instead of greater than. So I would edit that out if I were a editor of my videos, but we'll leave that in for no good reason except that I don't want to take the time to edit it out. So apparently my real values are non-zero at 0, 2, and 98, and my IMAG values are at 4 and 6. And so if we were to ask ourselves frequency vector of the real INDs, that corresponds to 0 Hertz, 20 Hertz, and 980 Hertz, which we should expect. And then similarly, the imaginary ones are at 40 and 960. So if I wanted to rebuild this thing based on that symbolic stuff, I could say that y, I guess I'm just going to call that rebuilt. I'm going to set it to zeros like t. I'm going to say for IND in real INDs, F is equal to freq of IND. If F equals 0, then Y rebuilt plus equals, how do I do this? Let's say that A, my current A coefficient, make this F sub I and A sub I. So A sub I will equal the real of Y FFT evaluated at IND. And so if we're talking about the 0 with frequency, then we have to divide that by 2. Like I said, that's the quirk of how the FFT works. I can't necessarily give you a good reason for that, but the DC value would need to be divided by 2. If it's not a DC value, then we're going to add to it A sub I times the cosine of 2 times pi times F sub I times T. And I think that, and then we'll do something similar for the IMAG INDs. Only we don't need to So I'm going to put a -1 right there, and then I'll do a plus equals b sub I times the sine of 2 times pi times f sub I times t. And so then we want to go back to figure 1 and plot t comma y sub rebuilt. And do that as a black dash dash line. And I seem to have a scaling problem. So what's that about? Okay, I'm back and I figured out what the problem was. The issue is that because I didn't filter out the aliased terms, I have double the amplitude of what I should have. So in both cases, I'm going to say if IND is less than n divided by 2, where n is the total number of elements. So n divided by 2 should be the index of the Nyquist frequency. I only want to consider terms that are below that. So if I make that change and rerun my code, I have there my recreated waveform directly on top of my other waveform. And again, I've got some B coefficients. I guess I never really specifically find the B coefficients. And the A coefficients, I don't put them in a list or anything. Well, let's do that real fast. So if I said, here's my A list and my freak list sub A. So I'm going to have A list dot append A sub I. Excuse me. My freak list sub A dot append F sub I, and then do those things again. Oops. So now when I run the code, I have that. So freak list sub A and A list tells me that I've got values of 14 and 3 at 0 and 20 hertz. And based on what I know, 3 at 20 hertz and 7 times 2 at 0 hertz makes sense. And I'll have a freak list B and a B list of magnitude 5 at 40 hertz, and that also makes sense. So if I combine those pieces of information, I can get back my symbolic expression, which is the goal of the lab.